Well, good morning, everybody. Happy Monday? No? No. No, it's just all Garfield today. Just don't like Mondays. This week in physics, let's see. Today's the end of chapter, whatever it was, 6, and then start of chapter 7, maybe all of chapter 7. And then Wednesday, finish up chapter 7 and definitely chapter 8. Chapter 8 is kind of like the big chapter of the 7, 8. There's really two topics in this unit. There's Newton's laws, which are chapters 5 and 6, and then there's conservation of energy, which is chapters 7 and 8. And then this Thursday, we're doing lab 5. We did lab 6 last week, so why not lab 5 this week, right? So that's kind of where we're up against. And then is your exam next week? I think your exam's not a week from this Thursday. I'm pretty sure that's what it is. Yeah, now the panic sets in, right? When's the 10th? 2 weeks. I was scared because I haven't written a darn thing yet. What? 2 weeks from this Thursday. I just made myself look good, right? I threatened you with something and then said, no, it's too. No, that was a mistake. I forget. We have lab 7 to do still. That's what I was forgetting. It's 6, then 5, then 7. All right, now that the adrenaline is rushing through your veins, let's finish up this banked curve. It was this banked curve problem, right? Okay, and part of the issue with this situation is the fact that our acceleration, right, in this horizontal circle, right, as we're going around like this, that acceleration is directly horizontal. So which way do we want to set up our coordinate system? What do we always follow? We follow the acceleration, don't we? So if we say, okay, well, this has to be positive x, positive y, it has to be perpendicular to x. We now are in a situation where 2 out of our 3 forces on this screen are not playing nice. In fact, really, this is kind of the first example I'm doing where we don't find components of mg. See how mg is directly up and down? And we've said positive y is directly up and down. So again, sort of what I visualize is like a coordinate system that's centered, right, on that object so I can see what all the forces are doing. And if I look at my blue dotted lines, I'm like, oh, mg doesn't have components. But now the normal force does? I haven't done this. So if this is the angle theta right there, right, then how do I know what angles are which? I'll put you out of your misery. I'm not going to show you how to do it. It's geometry. It's working your way around parallel lines and some other things, okay? But it turns out that this angle right here is theta. And then this angle right here is theta. And you can just trust me on that one, right? Okay. All right. So with that in place, we can now go and find some components, right? Because we're going to have a component of the normal force that points up and horizontally. And then we're going to have a component of this frictional force that points horizontally and down. So when it comes to writing out Newton's second law, right? So we're going to do this, right? And we're going to do it in the x and y directions. In the x direction, we have the mass of the vehicle times its acceleration in that direction. And in the y direction, I just write 0 equals. And why do I write 0 equals? I made sure that the acceleration was only in x, right? It's the whole, that we're paying this price of having to go find some components now of forces. Believe it or not, finding the components of those forces is easier than dealing with components of acceleration. Okay, so what are these components? You choose friction or normal force first. Which ones do you want to find? Normal force? We got to do both, doesn't matter. Okay, so the vertical one. I go straight for that vertical normal force because it's touching the angle. Anything's touching the angle is what? Cosine, n cosine theta, which makes the other one n sine theta because it's not touching. And it can really kind of be that quick if you can trust that touching, not touching thing, right? The hard part is maybe finding where the angles are. But I think I've shown you now how to find all angles everywhere. All right, and then as far as the frictional force is concerned here, the horizontal one, is it touching or not touching? It's touching, so cosine. And this one will be F sine. Okay, so now that we've got all that written down, and this is horribly messy, x direction. Again, I'm just going to concentrate like in this direction. And as far as I can tell, I see two forces right there. Looks like I've got an n sine theta and an F cosine theta. And then in the y direction, come along here, I'm looking sort of up and down this line, and I see that one, and mg. No, sorry, this one, the n cosine theta, the F sine theta, and the mg. So I've got three of them there. So n cosine theta, F sine theta, and mg. N is pointing up, F sine theta pointing down, mg pointing down. I never checked my n sine theta. These are both positive. They're both pointing to the right. And I've got now some equations written down. Notice I haven't gotten all tied up and worried about what I'm going to solve. The analysis, the visualization, the strategy is all about getting the picture, finding components, getting those force components written out correctly with their signs. And now I can take a step back and figure out just what the heck they want me to find. We're going to find the speed. We're going to find the speed that it's safe, right, to do something like that. Okay. We talked about this last week. Does anybody remember what kind of friction that is? Kinetic or static? That's static. That's static friction. The friction between the wheels of a car and the road is static unless you are told that it's like skidding or slipping, right, or sliding. It's going to be static. All right, so we know that that's static friction. Static friction is kind of scary, but let's not worry about that till later. Speed, right? The speed at which like this bus or this car can safely round this corner. I don't see any speed in here. Yeah. Did I do something wrong, or do you have the answer? Well, I have the answer. Where's the speed? It's hidden in the mass times acceleration. You can turn it into v squared over r. This is a circle, isn't it? This thing's not sliding down the slope. It's driving around in a horizontal circle. And so that means that my acceleration is centripetal, pointing towards the center. And way back from chapter 4, we have a relationship between that acceleration and the speed and the radius of the turn. Okay, so so we got to find acceleration to be able to find the speed. Great, we got to solve this for acceleration. I only see one acceleration up there, but I don't know. Let's assume that we are told, just to help you, that we're given an angle. Okay, that's known, and the coefficient of static friction is known. And we're given the radius of the turn. Okay? Right. Thank you very much. You beat me to the pun. It's good to know the younger generations can still do it. It's pretty fun, right? So that's where the coefficient comes in, and this is where we start being able to eliminate, like solve out, right, the normal force, like swapping it out for things. So I can, let's see here. This gets a little bit hairy, right? Let's Okay. Mathematically, I think what I'm going to do is I'm going to substitute in that f right there and then solve this equation for n. And once I have that n, I'm going to plug it in up there. Substitute in my v squared over r into there, and then solve for v. I don't want to take the time to do that this morning. And so I'm going to do a step which drives my students bananas. And it's, have I showed you this before? It's called the AMO step. Have I done this in here? No? Does anybody know what AMO stands for? A miracle occurred. Okay? This is the step I pull out whenever I don't want to do any, I don't want to spend time on algebra, okay? Because I've got more important things to do. And in doing all of the algebra that I just outlined, okay, this is what you'll get. This is the punchline. You get the square root of r times, now it's bad news when I draw a really big square root, isn't it? Okay. It's the radius times little g, okay? And then a big mu cosine theta plus sine theta all over cosine theta minus mu sine theta. It's really bad. Okay? That right there, this horrible thing in the box, okay, is the solution for any vehicle that is going around a banked turn of really any angle, okay? And let's see if this, like, let's see if there's some things that we can pull out of this. I've checked it, but there are some other checks that you can kind of do in there. Not so much checks, but implications, okay? And I think maybe one of the first things to look at is what happens if the turn is flat. So if the turn is flat, if it's not banked up, right, and this car is just going around a normal flat turn, then what happens to this equation? Let's do some what ifs, right? If theta equals 0, then what does this equation turn into? Okay, what is cosine of 0? It's 1. So that's mu times 1 plus, and what's sine of 0? 0. And cosine of 0 we always said was 1 and minus 0, right? So this turns into the square root of rug. RGU, RUG, GUR. Okay? That right there is the tangential speed that a vehicle can have. That's the maximum speed a vehicle can have and maintain connection with the road. Any faster than that speed right there, and the vehicle will start skidding. Okay? So, coefficient of friction is defined by surface properties, how warm the tires are, if there's ice on the road. Like, what happens to mu if there's ice on the road? Does it get bigger or smaller? It gets smaller, right? And so that means that the speed that a car can have and safely make it through the turn goes down. Anybody that's ever driven over black ice knows exactly what speed you can be going and still be turning. The answer is 0, right? Like when you have a frictionless situation, there's on a flat surface, there's no way to make that turn. So there is like a maximum speed, and it's determined by radius of the turn, the planet that you're on, and what your coefficient of friction is going to be. All right, so what's another thing we can play with? What if, let's go back up to the black equation. What if friction disappears? So let's answer the question, okay, black ice, is there a speed other than 0, right, that one can safely make a turn if it's not flat, right? So if we do the case where mu equals 0, right, then what does this equation become? Well, we have r times g Mu is 0, which leaves me with a sine theta all over a cosine theta, doesn't it? And what's sine over cosine? So it turns out there is a non-zero speed that a car can safely go around a turn if it's on a frictionless surface, as long as the turn is what? What do we need inside that square root? An angle, right? Here on the West Coast, almost all of our roads, turns in our roads have banks to them. Part of the reason for this is because we are rather new when it comes to building roads out here in the West, and a lot of our roads were built within the last 100 years, and we have this technology. Like our roads were built more or less after cars were invented. If you go to the East Coast, a lot of their roads, unless they've been redone, are flat, okay? And like almost perfectly flat. And when there's a turn in the road, okay, they don't bank the turn, okay? They also don't have, there's these things that don't exist on the East Coast, they're called mountains. I've been to the East Coast. I've been to the mountains of the East, okay? And they're hills. They're just hills, right? But in all fairness to people from the East Coast, you know those things out here we call rivers? They call them creeks. Because on the East Coast, a river is basically an ocean moving in one direction, right? Anybody that stood on an East Coast river, like, you can barely see across them, okay? And then, like, container ships start floating up the river. You're like, the only thing we have floating up the river here in the West is, like, salmon or something. Okay, so so what happens on the East Coast, like you're driving in Pennsylvania in the winter and you hit a patch of black ice and there's a turn? Yeah, you end up in the ditch. Okay, that's why they put ditches on the side of the roads, to catch all the cars. Here on the West, you go to the mountains and we bank our turns, right? And that's just increasing, right, the safe speed at which you can execute that turn, even if the coefficient of friction were to go down. Please don't do what my mother did once. We were driving up to Yosemite in the middle of the winter, and it was snowing, and there was snow on the road. And at some point, it wasn't really her fault, there was a situation, but she ended up, as we were going around a turn, she ended up pulling to a stop. Once you stop, and the coefficient of friction is not good between your wheels and the tire, which way are you now? Where are you going to end up? Which way is your acceleration go now? We are just a tomato sliding down a more or less frictionless surface, aren't we? Into the snowbank that's on the bottom side. And guess who got to get out and unbury the car? Yeah, me and my uncle. This is what the story was. Yeah, it's easier to just keep going. Wasn't really my mother's fault. The cars in front stopped, and anyway. All right, so I know that was a little bit like hand wavy there and that I didn't do a lot of math on the screen, but I just wanted you to be armed with this. Like basically, if it's a banked curve and the car's not skidding or sliding, which we wouldn't give you a skidding or sliding version, right? You can use that. You just need to be able to make sure that you figure out angles and things. So they might ask you for what the coefficient is that's required for a certain speed and angle, which will require massaging that result right there. But we basically kind of solved every banked turn problem, which unlike most, Newton's laws problems, I've told you've got to set up each problem individually because the forces are all different, right? But when it comes to this specific example of a car going around a banked turn, that's basically all there is.
Is this like the Frankenstein tool where we don't have to reinvent the wheel and we could just like...
Yeah, as long as they don't, and they won't, we won't do this to you, but like if there was an additional force acting on this car somehow horizontally or vertically or something, right? We'd have to be more careful. But as long as the car is just normally going around a curve and that curve has a bank, or even if it's flat, You now have the flat version in the blue, right? You have the frictionless version in the red. That all applies. All right. Remember when we did projectile motion, bless you, and I gave you the, like, an equation for solving for the initial velocity, right? And then we kind of like solved all the problems where you didn't know the initial velocity. It's a little bit like that, right? Physics is often after, if we can, we tried to solve just the problem once and then apply our knowledge to various situations. All right, that was the end of chapter whatever we were in, 6. I don't know good with numbers. I really just can't figure it out. So this is going to be a transition. This is different, okay? What have we done so far? Okay, so in this class, you've been given 2 toolboxes. You've been given the toolbox of kinematics, the kinematic equations, which allows us to solve for things speeding up, slowing down, figuring out how long it takes things to happen, like time-wise. And then we gave you the toolbox of Newton's laws, which allows us to go in and take a look at forces and figure out the acceleration of an object so that maybe we can then apply our kinematics. Well, I'm going to introduce you to the third toolbox now. Third out of the 4 toolboxes we give you in this class. So this toolbox has to do with energy. And okay, so what's energy? No, that's motion. Let me ask a different question, one I know you can answer. Give me an example of a type of energy. Heat, light, kinetic, chemical, potential, nuclear. Okay? You can name kinds of energy. That's great. But when it comes to what is energy, we have a little bit of a problem, and it's the same problem we have when it comes to defining what mass is. What's mass? Tastes like salt, right? Right? Okay. It's hard. Like we know what it feels like to work against our mass. We know that there's a difference between our mass and our weight, because weight is the force of gravity acting on something, where mass is intrinsic to the thing. But and as many of you already, spoiler alert. Right? Which we won't get to until physics 4C, okay? But our modern conception is that energy and mass are 2 sides of the same coin. We can convert between them a la atomic boom boom, right? So it's no surprise that trying to define what energy is in words is a little bit difficult. We struggle with defining mass in words, right? And so, Paul Hewitt of the City College of San Francisco, one of my kind of heroes when it comes to teaching this stuff, okay, said this in one of his textbooks. We don't use his textbooks because they are more geared towards sort of a high school and college level conceptual only class. We call it the Physics for Poets class. That's what I call it, the Physics for Poets class. The physics class that all the English students would take because the college tells them they have to be well-rounded and take a science class, right? Here we call it Physical Science 11, I think. Anyway, I haven't taught that class in years. But he said this in one of his textbooks, and it's always stuck with me, right? In terms of this idea about why energy is useful and what it does and what its function is. And so I give that to you, right, for your consideration, right? And because we're going to talk about getting things moving. Right? We've talked about it from the point of view of Newton and forces, right? These pushes or pulls on objects. Now we're going to get a different tool that, though it involves forces, and we'll continue to talk about forces, this tool is going to save us from some of the complexity that Newton's laws. What's the bad part about Newton's second law? Like really, what's the chief headache? You're allowed to say all of it, but in particular, you're all hovering around the same problem. Vectors. Right? If we didn't have to worry about directions of things, we wouldn't have to find components of things, right? And that means no trig, right? And if we could just please, Mr. Balogh, pretty please go back to just adding and subtracting numbers, my life would be better, right? Guess what energy does? Gets rid of the vectors. Yes. Okay, so how are we going to do it? All physics textbooks do this wrong. Note that I did not say the books are wrong. I said they do it wrong. For some reason, they feel like they need to drag you through this concept of work, and we'll get there. We're going to do work. But they never tell you where you're headed, like in chapter 7. It happens all the time, okay? So I want to show you the end. I want to show you what we're going for, right? So that we have a lighthouse. We have a goal, right? And this is where we're going to get. I don't know why they should start with conservation of energy, then go into the nitty-gritties, and then finish with conservation of energy. So that's what we're going to do. So again, spoiler alert for chapter 8, okay? But this is really important for you to have context of what's going on, okay? What does it mean to conserve energy? I mean, there's when your parents yell at you to turn the lights off or whatever, right? Okay? But it's not that kind of conservation we're talking about. By the way, turn your lights off. That's a property, right, of energy in that there is a set amount of energy that this universe has. And there is nothing the universe or we human beings can do to change that. The amount of energy is fixed. As a matter of fact, I get really upset sometimes when people keep running around talking about the energy crisis. What's the energy crisis? We're somehow running out of energy or something, right? Last time I checked, the amount of energy in the universe is a constant. What's the only thing we can do with energy? We can change it between the forms that we already talked about, right? And just to be clear, let's talk about the. Just make a list. We'll do kinetic energy. You know what? No, we won't. We'll break that down later. Okay. Let's just call it mechanical energy. Okay, and then was another electrical. I heard out there. There was chemical. There was nuclear, and there was thermal. And I'm going to leave a big space between there for reasons that will become clear later. Okay, so those in general, the kinds of energy that exist out. So mechanical would be things moving. Storing energy in the gravitational potential energy. Electrical would be anything that has to do with electrical circuits, charges, making electrons do our bidding. Chemical, the energy stored in chemical bonds between atoms. Nuclear being the energy that's stored within the nucleus of the atom, keeping protons together and all that, neutrons and protons together. And then thermal energy is this sort of catch-all term that we use for thermodynamics, the energy associated with heat, and more typically the energy that's associated with lost energy. Because I did this in order, but thermal energy is the least useful form of energy that we have. Think about it this way. When was the last time you saw a car going down the street running on air temperature? We work really good here in Fresno, right? Okay. But thermal energy, the temperature of the air, the temperature of materials, in general is the least useful. We can kind of do stuff with it, but we're way more efficient the further up in that list that we go. Okay? So we can transfer energy around, but the amount of energy stays the same. And I get upset when people say there's an energy crisis. Now, full disclosure, I was born and raised in Santa Cruz. I'm a tree hugger. I kiss banana slugs, blah, 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 blah. Save the planet, go green, let's go. Okay? But we don't have an energy crisis. We do have a crisis. We're changing our environment in ways that we don't understand and we're having a hard time keeping up with now, right? So that problem needs to be fixed and mitigated. It's not an energy crisis. It's an entropy crisis. We're running out of forms of energy that are easy for us to use, like gasoline. Well, not so much running out of it, as the use of that form of energy is causing bigger problems, right? And so we need to work on that. But when we come back to it from a strict physics point of view, you can never get more than what you start with. And that's what that statement says. For any situation, the amount of energy you begin with is going to be the amount of energy you end with. And that's broadly overall true in the universe and here on the surface of planet Earth and everywhere. Now here comes the but. But we can define a system, a collection of objects, a situation where it appears like energy isn't being conserved. Driving your car, okay? Your car's going along at some speed, and if it's moving along, what kind of energy does it have? Mechanical energy, specifically kinetic energy, the energy associated with motion. We'll get into this later, okay? So it has some amount of energy because it's moving. And then you slam on the brakes. How much energy does it have when it comes to a stop?
In terms of mechanical energy,
The mechanical energy disappeared, didn't it?
yeah.
So I just broke the rule?
No.
Where'd the energy go? Into heating up the thermal energy, right, of the disks, didn't it? But what we're going to do is we are going to allow for energy to be lost to a system, to a specific. So in other words, if I want to concentrate on the mechanical energy of the car, I would say that it does lose mechanical energy to thermal energy, and we're not going to kind of keep track of that. We don't know yet how to do that. That'll come in Physics 4C, okay? So it's going to be kind of weird because you'll be sitting there going, but energy is conserved. Why do they keep telling me on YouTube or in the book or Mr. Bear, why do you keep saying the energy is lost? What we mean by that, it's lost to another form that we haven't figured out, we haven't taught you how to keep track of yet. And for chapter 7 and 8, we're going to live in mechanical energy land. In Physics 4B, we'll start tackling electrical energy. And in Physics 4C, we'll get to chemical, nuclear, and thermal energy. Okay? So for Physics 4A, we're living in this regime of mechanical energy. We're going to talk about kinetic energy, the energy associated with motion, and potential energy, the energy that's associated with like a state or a location of an object. And we'll kind of limit it to that. And any time that there is a loss of energy, let me just do another example, okay? So if I take this tennis ball and I hold it up, it has gravitational potential energy. There's something about this ball that when I let go, what's going to happen? It's going to start moving, isn't it? And so if it starts moving, what kind of energy is that? It's still mechanical, but instead of potential, it's kinetic, right? So the ball converts some sort of potential energy that it has here because of its position into the energy of motion as it falls, right? So if it starts with 10 units of potential energy, by conservation of energy, how many units of kinetic energy must it have before it hits the floor? 10. It's conservation of energy, right? So if I let go of the ball and I let it bounce, how much potential energy does it have? Well, it's on the floor, so 0. How much kinetic energy does it have? Well, it's not moving, so 0. So 10 turned into 0. I just broke the universe. No. What happened? Energy was lost to my system, because I narrowly defined my system, right, as mechanical energy. And where did the energy go? Into heat, as it changed the shape of the ball as it bounced at the floor. Yeah, good. There's sound waves that are happening, right? And so energy is going into sound waves, right? There's a little bit of friction, all that kind of stuff. Friction. Friction is going to be the big stealer. Friction is going to just always be taking stuff away.
What is friction in terms of energy? Is it like a thermal energy, or?
It ends up turning stuff into thermal energy.
Okay.
Sound is a form of mechanical energy we'll get to in physics 4C. There are times I just want to dump everything on you, but then I don't, you'd all drop. So I'm trying to protect you while simultaneously trying to give you the big picture. I'm not sure it's working. So this is the law. Conservation laws are built into the fabric of our cosmos. As human beings, we've discovered these ideas about we have a set amount, we can only just convert back and forth between types, right? Another conservation law we'll hit this semester will be conservation of momentum. We'll get to that after the exam. But that is the law. Now, in general, when we have losses of energy to forms that we don't know about, we are going to call that loss, or we're going to characterize that loss as this thing called work. Okay? And so the form of conservation of energy that you are going to see over and over and over again is the one here in the double box. Okay? Where I've added a term. I've attached, right, this work, and that subscript there is supposed to say other. I just can't spell. Okay? There is an H in there, I promise. Where there's some other either extra source or extra sink, something that's either giving energy or taking energy away, that we are going to acknowledge as existing but not get into the nitty-gritty details of. So you just need to kind of hold on for that ride. And now what we're going to do is we're going to start in chapter 7, which is all about this work. It's all about this idea that we can put in or take energy out of a system if we kind of narrowly define the system. I mean, think of it in terms of your car again. How much kinetic energy does your car have sitting at a stoplight? 0. You're not moving. You hit the gas, right? And now you're moving along. Do you have kinetic energy now? Yeah. Where did it come from? It came from the chemical energy bonds in the gasoline that your engine is breaking down, right, to get you going. We don't want to talk about chemistry, right? Right? Okay, right? So we're going to call that work other, right? There was some amount of energy that came from the gasoline magic, right, that we're not going to worry about because we want to concentrate on how that car got kinetic energy. It got it from the work that the engine did. Remember, I'll kind of do this I'll be pointing out as we go along, right? We got this energy, we got this, and then we've got this work, right? That's doing something else. Rocket engines do work on rockets to give them give thrust, to get them going places, to give them kinetic energy, to change their potential energy. Brakes do work other to take energy out of the system. It's going to be like the recycle bin on the desktop, where just anything you don't want, you throw in there, okay, and deal with appropriately. Okay, so that's kind of the big overall picture that we're going for with conservation of energy. And now it's time to talk about work. Sucks to be them, huh? This obviously is like, a photograph is always just a single moment in time. We don't know. I can think of 3 possibilities that are taking place right here, right? That car is either being pushed up the hill or is sitting still and they're just kind of holding it there, or they are losing.
I like that one.
You like that one?
Yeah.
We need to talk, Liam. All right, so work. When I say the word work, what sort of trauma do you have associated with that word? You think immediately of the thing you need to do to make money, to do whatever, right? So that you can pay your taxes, so that you can then make more money so you can pay taxes, and then we die, right? Work has good and bad connotations in our society. You're taking a major so that you can eventually get a job, so you can work, so you can do something, right? And that's not the work we're talking about. Okay? We are talking about mechanical work. Mechanical work requires motion. It requires an object to be moved over a distance, some distance. If they're neither pushing that car up the hill or letting it roll back down, if they're just holding the car in place, is any mechanical work being done? No. And you're like, but Mr. Balogh, they can't hold it up for forever, right? I mean, am I doing any work right now? Not zero mechanical work. And how can you tell? There's no distance being done. There's no motion here, right? Okay. But can I hold this up all day long? I'm going to run out of calories eventually, right? That's biology. We don't want to do biology either, right? Some of you are like, yeah, we can do some biology, Mr. Balogh, right? No, we don't want to do biology. It's a physics class, right? So there's biological work and some stuff that happens in chemistry, but specifically, okay, when it comes to this class and in engineering, mechanical work, okay, requires that there be some sort of displacement. In other words, if I take an object, how do you get an object to go somewhere? Push it. Okay, what are we now talking about if we're talking about pushing stuff? Forces. Oh boy. You said, Mr. Balogh, that there's no more vectors. Well, they're there, but we're going to get rid of them. Don't worry. Okay? So we take, I don't know, a wagon, something, right? Pushing along the ground, right? So you got the ground pushing along, right? And this wagon goes some distance. I think your book uses S as a generic displacement vector. It's fairly common. We'll go, I like D myself, but whatever. Okay? We don't want to say X, we don't want to say Y, even though this is purely horizontal, we could change this, swap this out for X, but we don't want you to get locked into thinking it can only be horizontal, right? Okay? So we're applying a force, it causes this thing to go some distance S, okay? We would say that the work is the product, the multiplication of that force times that distance. Mr. Balogh, you wrote that wrong. Because No vector sign on the left. There's vectors on the right, but there's no vectors on the left. For those of you that have been through this part of your mathematical career, what did I just write down? The dot product. The dot product is a way of multiplying vectors together. We've talked about in this class about adding vectors and subtracting vectors, right? But then there was that part of chapter 3 that I said skip over. We're going to get back to it later. Well, later's now. Okay? And we need to talk about multiplying vectors together because now we're up against having to multiply vectors together. And there are two ways, turns out, to multiply vectors together. One way, called the dot product that I have here on the screen, gives you not a vector. Gives you a scalar. Scalar is a fancy word for a number. Okay? So this is sometimes called the scalar product also, but dot product is a more normal term for it. It's a way of multiplying two vectors together so that all you get is a number out with no direction associated with it. The other way of multiplying vectors, I think you can guess. It's a way of multiplying that gets you another vector out. It's called the cross product. See how there's a dot between those two? In a cross product, which we'll get to later, we use the symbol x, the multiplication symbol x, right? And that's why it's called the cross product, because we call that the cross. All right, so that will give you another vector. This will give you another vector, but the dot product does not. In that sense, it strips away the vectorness. So what is work? Is it a scalar or a vector? It's a scalar. What's energy? It's a scalar. Okay? Which is nice, because then we don't have to worry about directions. But what is going on here? How do we like magically get, and how do we do that, and all that kind of stuff? Okay, so let's take a, okay, so all I drew in that diagram was the force that was propelling this thing to the right, didn't I, right? The distance here that it went, okay, directed towards the right. I don't know why I just drew two, anyway, okay. I didn't draw friction. What if this thing had friction? What if friction, and it was sliding, so we'll say it's kinetic friction, okay? What can you tell me about the work that capital F is doing compared to the work that friction is doing? Is there something different here? The magnitudes are different slightly, but there is kind of a direction there, isn't there? The propulsion, the pushing force is making this thing move, but what is the friction trying to do? Make it stop moving. When the force and the displacement are in opposite directions, that work is defined as negative. Positive work, when force and direction are in the same direction. Negative, when force and displacement are opposing each other. And we haven't even gotten into the normal force and gravity. Oh my gosh, this is getting worse. How much work is the normal force doing? Well, it's not positive because it's not in the same direction as the displacement. And it's not negative because it's not acting against the displacement. Oh, it is a constant. It's what constant? 0. 0 when the force and the displacement are perpendicular. Perpendicular? Did I spell that? Perpendicular. I don't know how to spell perpendicular. Okay? It's physics. We spell fun, P-H-U-N. Okay. So, positive work in black, 0 work in blue, negative work in red. How do I keep track of all of this stuff? Answer, dot product. The dot product captures all of this. Let me show you how that works. Yeah, you guys waited too long. You get F's. Okay. What is the dot product? Dot product, okay, or scalar product. There's two ways to go about sort of dealing with this, okay? And we're going to do both, okay? You take two vectors and you multiply them together with the dot product. You can find what that dot product is by taking the magnitude of one vector multiplied by the notice there's no vector signs over those, right? Just magnitude minus magnitude times the cosine of the angle between those vectors. This is kind of important for you to understand. If I've got a vector like that and I've got a vector like this is the angle between them. If they say that the angle of A is 30 degrees and the angle of B is negative 15 degrees from the positive x-axis, what's the angle between them? 45. Do you see what happened there? You got to be careful about the angle between the vectors, right? But it can be found this way. It's fairly useful, sort of a kind of a quick way of doing it if you know the magnitudes of the vectors and the angles that they are pointing at. But there's other ways to express vectors. And the other way that we use in physics a lot is with that unit vector notation. Okay? But before I get to the unit vector part of it, let's go back and look at this, right? We know that a dot product is A times B times cosine theta. So if we did this with the work equation, right, that would be magnitude F, magnitude S, or the displacement, whatever that is, x, y, z, times the cosine of the angle between them. What is the angle between F and S for the black? It's 0 degrees, isn't it? They're pointing in the same direction, so the angle between them is 0. And so what's the work going to be? F times S. Just if you know the magnitude of the force and you know how far it went, boom, you've got the work. Okay? What's the angle in the blue? It's either positive 90 or negative 90, isn't it? But it's 90 degrees. And what's the cosine of 90? 0. And so we get 0. And what's the angle for the red? 180, right? We've got a forward pointing displacement, but we've got a friction acting 180 degrees different from it. And what's the cosine of 180? Negative 1, so we get negative force times distance. So this definition of the dot product, there we go, encapsulates what we've just talked about in terms of work, right? When forces and distances are aligned, positive work. When they're opposite each other, we get negative work. And if they're at right angles to each other, we get 0 mechanical work. Okay. The other way of doing this, where we can write vectors as like they're in their component forms. Ooh, come back here. B would be B x I hat plus, and I'll just do this like in general without numbers for right now. Okay, let's just see what happens. Let's see what happens if we were to just sort of innocently multiply these two things together, right? We're gonna do this multiplication. So what does that get us? That gets us that thing times this thing. I plus B, Y, J. This is going to be really mad. You don't have to write down all of this. You just write down the punchline if you want. Okay. Given that thing on the screen right now, and knowing what you know about algebra, what would you do? Foil, distribute, blah, 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 right? Okay. You got to take you take this one times that one, right? And then this one times, this one times that one, and then this one times that one, and then this one times that one, right? And okay, let's write all that out. That's going to be AXI times BXI plus AXI times BYJ plus AYJ times BXI plus AYJ times BY. Okay, I think I made it. AX and BX are just numbers, aren't they? This is just a magnitude right there. The only directional thing are the I hats and the J hats, aren't they? So the only question we really need to answer here is, what does it mean when you do a dot product between two unit vectors? Well, first of all, a unit vector has magnitude of 1. So what's 1 times 1? 1. And what is the angle between I hat and I hat? 0. That's the same direction, isn't it? So what's the cosine of 0? It's 1. What's 1 times 1 times 1? 1. Or, in other words, in this case, it would just be, in the wrong color, AX BX, wouldn't it? This is 1 times 1 times 1 for that I dot I. But what is I dot J? What do we know about the I hat and J hat vectors? They're perpendicular to each other. So what's the dot product? 0? And why am I smiling? Because 0 is better than that mess up there. Okay, next term's got a J hat and an I hat in it. What's the automatic answer? 0. And then the last term has J's and J's. What's that going to be? It's just 1 times 1 times 1 again, isn't it? So this is AYBY. In other words, you can find the dot product between two vectors by taking their components. Write down the correct component, Mr. Balogh. In other words, like AX and BX, multiply them together, and then do the same thing for the Y's. I keep writing B first. AYBY. And then if there were Z's, okay, I won't write that one down, right? And that's another way of getting exactly the same answer. In fact, you can find the angle between vectors by doing both of those boxes. Because you can set these two boxes equal to each other and then solve for the angle between those vectors. It's very powerful. But notice what the dot product is doing. It's answering a question. We just have to figure out what question it's answering. We know how to get the answer, but what does the answer mean? The dot product asks how much of the first vector points in the same direction as the second vector. Some mathematicians might argue with me about the ordering of that sentence. But that's really what it asks. How much, look at this, how much of I points in the same direction as I? All of it, 1. That's how you say that in math, okay? Right? How much of I points in the same direction as J? None of it. How do you say that in math? Okay? That's what the dot product does. So that when we go back to work, right, and we're asking ourselves a question, how much of the force and displacement are aligned with each other, right? If they're both exactly aligned to each other, we'll get the maximum amount of work. If they are opposite each other, are they aligned? I mean, they're opposite, they're all along a line, right? But we get that idea of like maximum negative work, okay? And then when they're perpendicular to each other, we're not doing any mechanical work at all. But what about all the in-betweeny cases, Mr. Balogh, right? What about like you got the thing and you, like if you're pulling a kid in a wagon, or you're doing the vacuum cleaner across the floor, or you're sweeping, or doing any other situation, which very likely is going to have a force pointing at some weird angle, and then a direction that that thing is moving, right? Well, how do you handle that? Find the components. Done. Or know the angle between them, right? And their magnitudes. Done. We can do this. We have the power. But what happens if the force changes? Does your car's engine apply the same force to the tires all the time while you are accelerating? No. Matter of fact, it gets progressively weaker. Like it starts off pretty strong and then it gets stronger, but then there's a limit to the engine of what its power output can be, and it's like as you get faster and faster, it's sort of its ability to apply for it. I'm lying a lot there, but that's the general idea. Okay? So the force, when you are applying that accelerator, is changing. How rapidly is it changing? Depends. But does it change every 10 seconds? Does it change every second? Does it change every 10th of a second? Or 1,000th of a second? Or infinitely number tiny time
per second?
How do we find the total work that's done by a car's engine as the car accelerates from 0 to 60 if that car's engine is constantly changing the amount of force that it applies? I mean, the distance is easy. It's just however long it rode around the ground, right? But how do I figure out what the work is if the force is constantly changing? Say it loud. An integral? Wait a second. Wait. Wait a second. A lot of you are panicking right now. It's okay. It's going to be all right. We can take that force and break and figure out what that force is over a little tiny chunk of distance and do that like over and over and add up all those bits and get the total work? That's exactly what that says right there. And for those of you who have been complaining to me, I thought this is a calculus-based class. All we've done is algebra and trig. I don't like algebra and trig. I don't blame you. I don't like algebra and trig either. For those of you, we've arrived, haven't we? We've arrived. We're actually not going to do this right now. But I just wanted, that is the actual definition of work. Okay? For a varying force over a varying distance, you can do it like that. Now, in truth, right, okay, there are limits on this integral, okay? Because we need to talk about something very important. What's this? Okay. Can do it with my eyes closed. My handwriting's even worse. All right. So, what just happened there? You turned a crank. Okay, that's what they called it in math. You turned a crank. You have been taught probably in your calculus classes to turn cranks. You did an algorithm. That's what you did. Okay. You went, this is I did +1. New number to this. I integrated. ChatGPT can do that. Wolfram Alpha can do that. Okay. Now, in your math class, you forgot something. What is that there for? Okay, right, because if you take the derivative, you could have a thing there, and then the derivative of a constant 0, and then... The universe doesn't work this way. The universe always has limits on its integrals. It just does. Those limits could be negative infinity to positive infinity, but they are still limits. That is banned in my class. Okay? If I see a plus c, it means you've not thought about your limits on your integral. I'm coming after you. But on paper, not at your homes. Be weird. So, limits on things. I don't know if this integral even works. So that's why we say, well, from some number to some number. Whatever that limit happens to be. Okay. That's enough of a... This is why I would not be a good math teacher. It's just not. I would work from the inside out to destroy the effigy of mathematics. It would just be, okay. We just did work done by a varying force, so now it's time for a quiz. Whee! About time. End of class. Boy. I didn't make it through chapter 7. So we will continue the theme of chapter 7 on Wednesday and start getting into chapter. It's actually okay. It's okay, because 7 and 8 blur together. And we'll get 7 and 8 started. We'll get 7 done and 8 finished. Because there really isn't that much for me to do here. Yeah. Need to talk about power. It'll be all right. It'll be all right. Oh, we have 2 weeks. So I keep thinking the exam is next week. I made an internal due date on my schedule that I had to have the exam written by next week. So I think that's why I'm flipping it. Today is the 23rd. Oh, I was supposed to finish chapter 6 today. What have we been doing? I could have sent you. No, we're going to send you home. But I do have 2 days. I got Wednesday and next Monday for chapter 7. We can do more. Some of you are like, no. Yes, we're going to do more. I forgot about this. On Wednesday, 2 days from now, what's the weather going to be like? We're going to run out of time for the quiz. Wednesday is going to be 95. It's going to be 102 tomorrow. It's going to be 90. Why are we checking the weather? We're going to go on a field trip on Wednesday. You're going to come to class. We're going to do some stuff in class. And then we're going to go for a field trip. Don't get excited. Bring your tennis shoes. If you can, if it's possible, wear something to run in. All right, let's do a quiz. 7.1, 7.2, 4 points. 4 points? What have I done? I don't know. I can't even look at. Stop doing.